Welcome to The Explainer. Today, we're diving deep into the invisible forces that literally shape our world, from the music we love to the energy that powers our lives. We're talking about waves and sound. They are everywhere, all the time, and you're about to find out exactly how they work. So think about this for a second. What on earth could possibly connect a gentle ripple in a pond, a single note from a guitar, and the deafening roar of a jet engine? They seem completely unrelated, right? Well, the answer is the fundamental science of waves. And by the end of this, you'll see that connection crystal clear. Let's get into it.
Okay, first things first. Before we can really get into sound, we have to back up and ask a more basic question. What even is a wave?
This is the single most important thing to get. A wave, or onde as you see here, is a disturbance that moves energy, not stuff. Think about a stadium wave at a game. People stand up and sit down. They don't actually run around the stadium. They stay in their seats. It's the energy, the idea of the wave that travels. That's a wave in a nutshell.
Now, waves pretty much come in two main flavors. On one hand, you've got transverse waves. This is where the particles move up and down while the wave itself moves forward. Like a classic ocean wave. But then you have longitudinal waves. Here, the particles get squished together and pulled apart in the same direction the wave is traveling. Imagine a slinky being pushed. And this one is key, because that's exactly how sound travels.
All right, so if we know what waves are, how do we talk about them? To compare the tiny wave from a whisper to the massive wave from a shout, we need a common language. So let's learn the anatomy of a wave. Turns out you can describe pretty much any wave using just four key things. First is amplitude. That's the wave's power or intensity. For sound, think volume. Then there's wavelength. That's its physical size, the distance from one peak to the next. Frequency is how often it comes at you, how many waves pass a point every second. And finally, period is just the time it takes for one single, complete wave to go by. These four things are basically a wave's unique fingerprint.
And what's really cool is that these properties are all tied together by this one super simple but powerful equation. A wave's speed, its velocity, v, is just as frequency, f, multiplied by its wavelength, lambda. That's it. This little formula dictates how fast energy is moving, whether it's light from a star billions of miles away or the sound from a speaker sitting right in front of you.
So of course, waves don't just travel in a straight line forever. They hit things, they bounce off things, they pass through them, and they even crash into each other. So what happens then? This is where it gets really fun. The simplest interaction is just reflection. When a wave hits something it can't go through, it bounces off. You see this with light hitting a mirror, right? Well, when a sound wave does it, we call that an echo. That is literally all an echo is, a sound wave bouncing off a wall and coming back to you.
But what happens when two waves are in the same place at the same time? Simple. They add together. It's called interference. If their peaks line up, they build on each other and create a bigger, more powerful wave. We call that constructive interference. But, and this is wild, if a peak meets a trough, they can completely cancel each other out into nothing. That's destructive interference, and it's the actual science behind how noise-canceling headphones work.
I guarantee you know this one, even if you don't know the name. The Doppler effect is the reason an ambulance siren sounds really high-pitched as it's racing toward you, and then the pitch suddenly drops as it passes and drives away. As it approaches, the sound waves are getting all bunched up, raising the frequency. As it leaves, they're stretching out, lowering it. Simple as that.
So what happens if you take that to the extreme? What if you go faster than the sound waves you're making? Well, then you get a shock wave. The jet is literally outrunning its own sound, and all those waves it's creating get piled up into this one massive wall of high-pressure air. And when that wall, that shock wave, passes by you on the ground, you hear it as a single explosive sound, a sonic boom. Okay, so we've covered the general physics of waves. Now let's bring it all home and focus specifically on how all of this applies to what we actually hear, the science of sound itself. So all those physical wave properties we talked about, they translate directly into the sounds we perceive. A wave's frequency, that determines its pitch, how high or low the note is. A wave's amplitude, that's its loudness. And finally, the wave's overall complexity, that creates its timbre, which is just its unique sound quality. It's how you can tell a trumpet and a saxophone apart, even if they're playing the exact same note.
Now, when we measure loudness, we use a unit called the decibel. The really important thing to know about this scale is that it's logarithmic. That just means it's based on powers of 10. So a sound at 20 decibels isn't twice as loud as 10 decibels, it's actually 10 times more intense. Our ears can handle such a gigantic range of sound that we need a scale like this just to make the numbers manageable.
The scale officially begins at 0 decibels. Now, that doesn't mean total silence. It means the absolute quietest sound the average, healthy human ear can possibly pick out, the very threshold of our hearing.
And then you go way, way up the scale to around 120 decibels. This is known as the threshold of pain. It's the point where a sound is so intense, it's no longer just heard. It actually starts to cause physical pain and can do real damage. The difference in energy between 0 and 120 dB is a factor of 1 trillion. Just shows you what an incredible instrument the human ear is.
Okay, for our last section, let's look at maybe the most beautiful and complex application of all this physics: music. How does all this science come together to create a symphony?
So think about a guitar string. How does it make a sound? Well, it's because of something called a standing wave. When you pluck it, the wave travels down the string, hits the end, reflects back, and interferes with itself. It creates this perfect, stable pattern that looks like it's just vibrating in place. That beautiful, stable vibration is the foundation of almost every musical note you've ever heard.
But here's where it gets really wild. A string doesn't just vibrate in one big way. It actually vibrates in multiple ways all at the same time. You have the main vibration, the big one. That's called the fundamental. But layered on top of that, it's also vibrating in halves and in thirds and in fourths. These extra vibrations are called harmonics.
And this is the secret sauce. The unique sound of an instrument, its timbre, comes from its specific recipe of that main fundamental note mixed with all of its unique higher harmonics. A piano and a violin can play the same note, the same fundamental, but they sound different because they have a different mix of harmonics. That combination is an instrument's sonic signature.
So there you have it. We've gone all the way from a simple ripple in a pond to the complexity of a symphony, all driven by the basic physics of waves. And remember, these exact same principles are at work right now in the light coming from your screen, the microwaves heating your food, and the radio waves bringing you a signal. So my final question for you is, what other invisible waves are you going to notice shaping your world? Thanks for joining us on The Explainer.